Beautiful. Hi, everybody. I'm excited to talk to you about this topic, and let's go. I will talk to you today about responsible AI as an umbrella term, and in particular, I will focus first on a subfield of it, typically themed algorithmic fairness. Okay. Attention currently in the general debate around computer science and AI, whether it is research or regulation, is on fairness. 10 years ago, the Obama administration's Big Data Working Group was perhaps one of the first initiatives that placed the emphasis on the problem of fairness. And here's a quote from the public documentation: discrimination may be the inadvertent outcome of the way big data technologies are structured and used. And so that brief pointed toward the potential of encoding discrimination in automated decisions. And that is probably one of the earliest instances of focus being drawn, attention being drawn to the topic of fairness. What has happened since? A lot of things. The topic of fairness moved from the margins of computer science research into the central, biggest kind of frontier problem in AI in general, in research, development, and governance. So there are new ethics courses for software engineers and also for people in any technology adjacent programs at primarily all major universities that prepare technologists. Fairness, ethics, hires in the industry are becoming common. So all of the major companies that engage in AI are also hiring people to specifically think about responsible AI, fairness, and ethics. ACM, which is the Association for Computing Machinery, the biggest kind of umbrella organization that organizes all of the key conferences. They started the Joint Task Force on Computer Science Curricula, and they're developing guidelines for teaching computer scientists, ethics, which initially, when this was first proposed, was met with some objections. It was previously thought that this is outside of what technologists and computer scientists should be thinking about. Initially, a very small symposium started at yours truly, New York University, called at the time Fairness, Accountability, and Transparency Symposium, became a major conference held every year across the world called ACM FACT. There are dedicated fellowships, grants, industry bounty competitions for finding bias, finding discrimination, finding ethical issues in the data and with the models, with money prizes offered to those that find them. Cities and governments start task forces for fairness and explainability in automated systems. And there are AI bills and resolutions. While in 2020, there was 13 states proposing AI-specific or machine learning-specific regulation. By 2024, such bills have been introduced in 40 states. And then there's the European Union AI Act, one of the key pieces of legislation. The Department of Justice is weighing proposals to examine AI bias in data collections and use. So this topic is very much central, hopefully I convinced you. Here's another metric. That conference that I mentioned to you, the one that was initialized at NYU as a small symposium, this is the rate of progression for submissions to that conference. So academic papers where people try to discuss topics of fairness. 71 submission in 2018. In 2022, it was 772. Now, couldn't find the number for 23, but this year it was 725. You would be compelled to say it's stagnating, but actually the case is that there are 4 more fairness and fairness adjacent conferences. So the demand for this field and for research in this field is huge. So what is the problem of fairness as it pertains to prediction, algorithms, machine learning, and AI? The idea was initially as follows. Outsourcing decision-making to machines is a good thing for ethics and fairness because machines will help us circumvent issues connected with human bias. That was the naive motivation that people initially were excited about. The reality, as illustrated here by a very infamous case of one particular algorithm, was dramatically different from what that promise would have you believe. So here you are looking at excerpts from a report published by ProPublica, investigative journalism, scientific research group, where they were examining a mock-up of a salient algorithm used by a company, North Point, that was developed in order to predict the risk of recidivism of people who were on trial for criminal offense. And so what these researchers found when they did their analysis with respect to fairness is that as the algorithm was applied to estimate what is going to be the risk of reoffense, the risk of recidivism, for people, as in this slide, with very similar prior histories, with very similar criminal histories of prior offenses and subsequent offenses, the algorithm would consistently predict significantly higher risk scores for Black people compared to white people, given similar or same data profiles. This case became so resonant in the field that nearly every presentation, every slide deck about fairness that you will see will probably have a reference, will probably have these pictures. It was, I think, a big wake-up call, starting in which all of the scientists turned their attention to this field and tried to figure out what is going on. Why is it that we were hoping to circumvent human biases and we ended up building systems that produce biases? More examples. Biases in translation. Some languages like Hungarian, Turkish, for example, do not have gendered pronouns. They have uniform pronoun for any gender. But as you do reverse translation into English, depending on what this pronoun signifies, it acquires a feminine or a masculine translated pronoun, where she is beautiful and he is clever, he reads, he builds, she saws, he teaches, and so on. So this is another example of a bias. Or a camera that suggests that someone's blinking, based on the person's ethnic heritage. Things like this, more recent examples with Midjourney, where the range of ages for subjects generated as a response to a prompt, man or woman, is also vastly different. So all of these problems that humans have for biases are multiplied and propagated with the machines that we're building. Other issues with bias, such as slower internet in certain neighborhoods that tend to be associated with certain demographic, ethnic distribution of residents, not explicitly designed to discriminate, but eventually having the effect of discriminating. Child abuse prediction model fails for families. Pittsburgh Child Welfare Agency goes full Orwell. These are many, many, many cases of how decisions aided by algorithms end up producing very problematic outcomes that have very strong associations with demographic group membership. Another recent example, Apple Card, two spouses with the same financial background, with same levels of education and same levels of income are applying for the same card, and one of them, typically male, gets 10 times the credit limit than the woman gets. Also, this example I want to pay attention to because we're going to talk about it a little bit later in the slides. Women less likely to be shown ads for high-paid jobs on Google, as study shows. Okay, so you may have heard about some of these examples. We're going to try to look closely at what exactly is going on here. So what are the sources of this unfairness? Typically, in conversations around this topic, you will have someone very quickly jumping the gun and saying, oh, I know. It's all about the data. The data is biased. Really, the algorithms cannot be fair or unfair. It's just a property of the data that you are using to train the algorithms. Algorithms are being trained on historical precedent, typically on historical decisions that have been made by humans in the past. So as you're learning the model, optimizing for mimicry of that past decision-making process, you are going to also learn the past biases of humans. So bias in historical decision-making leads to bias in the distribution of outcome variable that you're trying to predict for. For example, if you're predicting who's going to default, if you give them credit, or who's going to be a good job candidate, and you're learning from past CVs, historical CVs, and historically only men have been hired into the job, then your algorithm will learn to associate being a man, or some proxies for that, with being good at the job. Also, historical decision-making being biased leads to bias in the distribution of predictor variables as well. So the features that you're using on which you're basing the prediction. It could be due to animus historically, or it could be something not explicitly driven by bias or animus, but just structural inequality of who gets to access goods and beneficial outcomes in our society. Okay, for example, Amazon built an AI tool to hire people, but had to shut it down because it was discriminating against women. Same example that I gave you for the credit card before. You can think of them in this context to highlight the point that it's not necessarily bias, right? It's the fact that historically, maybe we have a century more of data on men being responsible financially for decisions, and then that translates to who gets credit on file, and then that gets fed into the training set. So you could say that's how bias comes in. But also bias in data collection practices, very important. There could be inequalities by class, race, and geography in what data does end up in the training sets. And typically we see inequalities in that the Anglo-Saxon world is generally the global north, and in particular America, are hugely overrepresented because this is where the research is, this is where the algorithms get developed. And so it is unsurprising that the American population is represented much more strongly. Okay, photos of bridegrooms from different countries aligned by the log likelihood that the classifier trained on open images assigns to the bridegroom class. Images from Ethiopia and Pakistan are not classified as consistently as images from the United States and Australia. So in other words, if I ask ImageNet what is on the right, they will say bride and a groom. And if I show the images from the left, it's going to say, I don't know, carnival. Another outcome of biased representation in our image training datasets. Same here. Which one is the kitchen? AI thinks it's only the one on the right. Okay, and then finally, bias in choice of target. Super important point that is very often underappreciated. As humans, we typically colloquially interchange terms, thinking they are relatively similar. Example with ProPublica, they were trying to predict recidivism, and they were probably training using historical data on people arrested for crime. Now, arrests are not equal to crime nor criminality. Arrests represent just that, arrests. They represent the police action of going somewhere and arresting someone. And that is not the same as rate of criminality. Medical spending being used as proxy for health. There is also an important case study on that. Here it is by Ziad Obermeyer, dissecting racial bias in an algorithm used to manage the health of populations. The bias that they found in this paper arises because the algorithm predicts healthcare costs rather than illness as a proxy. But unequal access to care means that we spend less money caring for Black patients than for white patients. Thus, despite healthcare costs appearing to be an effective proxy for health by some measures of predictive accuracy, large racial biases arise. Again, this is about what you choose as the target and how it's important to remember that it may not be accurately measuring the construct that you're trying to capture. Deborah Hellman, a researcher in this field, is saying, imagine that a life insurer is trying to decide what rates to change. Younger people get lower rates, older people get higher rates because they're more likely to die during the policy period and therefore to collect from the insurance pool. And on that basis, the insurer charges high rates to victims of domestic violence. Because if you're being beaten up, you're more likely to be killed, and therefore your heirs are going to collect the life insurance. I would describe that as a compounding and prior injustice. Now, while this is a stylized example, this is only a slightly exaggerated version of some of the logic that does get incorporated a lot of the times in how these algorithms end up affecting predictions over multiple cycles of their use and people re-entering the data having been subject to algorithmic predictions before. And finally, sampling bias. Who smokes more pot? Marijuana use, 18 to 25 years old. Blacks and whites use pot at about the same rate. But the arrests and the criminal charges for possession of marijuana are not happening at the same rate. Also, younger Black adults less likely to trust doctors and the healthcare system, unsurprisingly. Okay, so one takeaway that I would like for you to keep and refer back to as you're going to think about AI and technology is that the world as represented by the data is not generally the world as it is. So there are three key levels of representation that we can think about. There's the world as it should and could be. And then there's the world as it is with justices and societal biases that do occur. And then finally, there's the world according to data. And there's a distinction even between the second and third level. This distinction occurs depending on how I sample my data. If it's really, really difficult to become part of the data set, then the world according to my data will only contain people who manage to be sampled or to get access. And that's not going to be an accurate representation of the world as it is. Okay, so we talked about the usual suspect for the sources of unfairness, which is the data. And a lot of people will tell you, oh yeah, garbage in, garbage out. There's no such thing as unfair models. A lot of people feel very strongly. They're outraged when people say biased model. They will tell you, no, there's no such thing. Models are not biased. It's data that's biased. Now, I'm here to tell you that it's not entirely true. Yes, to a certain degree it is, but it's a little more nuanced than that. So the less usual suspect for the sources of unfairness is model specifications. There's this old adage, models are math, they cannot be biased, math doesn't lie. And the missed nuance in this is that model development is laden with value-based choices made by humans who have ethical access and preferences. Choice of the target, choice of the objective function, choice of the architecture, choice of the threshold, size of penalty for different types of errors. Do I want to optimize my model so that false positives are minimized or false negatives? To what degree do I want to balance this? These are all choices that go into modeling. And it so happens that different architectures and algorithms have different propensity to amplify class imbalance just by their geometric properties. So here's an example. Imagine that this is your data set. And first panel, I'm just going to look at majority group, demographic majority group. They all belong to the same class. And some of them in my data are labeled, for example, I don't know, defaulting on credit, and some others are not, something like that. And then you have a minority group, meaning minority in quantitative terms. There's fewer of them in the data. Their distribution in the same two-dimensional space is slightly different. So people who get positive outcome, again, are plus, and the negative outcome are the dots. Now, your model is going to try to fit the data by looking at them together, as in the third picture. So imagine that you're fitting a linear model. So you're going to try and build a model that finds the optimal position for a linear boundary that will separate positive instances from the negative instances. Where do you think that line is going to be? Because of how imbalanced these two classes are, the majority of points are green, minority is blue. The procedure that you're going to use, the optimization for finding that decision boundary, has no incentives whatsoever to even think about optimizing for the blue class. It's going to, without loss of much accuracy, just draw the same line as it did in the majority group, because overall accuracy is going to still be very high. And indeed, such a boundary would fit the green group very well, and the blue group is so small that inaccurate predictions on them kind of don't matter from the viewpoint of just optimizing the overall accuracy. So what this means is that the minority group is going to bear the burden of most errors, but the overall accuracy of the model is going to seem fine. Yeah, women less likely to be shown ads for high-paid jobs on Google, study shows. Why am I bringing this example again? This example is actually not as simple as it appears. There is a researcher, I'm blanking on the name, who did a study and discovered a very interesting and unintuitive reason for why this happened. So when you first read a title like this, okay, women less likely to be shown ads, my goodness, this is an outrage. Turns out that actually the mechanism for how that happens is not at all what you would think. Because there is a huge emphasis in tech companies on hiring a diverse body of employees, companies generally try to hire female candidates. They make an effort to do so. What this results in is that ad platforms, for example, if you're paying for ads on Google or Facebook or wherever it is, ad platforms realize that they can charge a premium for a certain pairs of eyeballs, right? So if everybody is trying to get in front of women and make women see these ads for jobs, what's going to happen is there's going to be a price premium for showing these ads to women. It's going to be slightly more pricey to show them to women because everybody's trying to do so. You have to compete with others. Now, placement of these ads happens algorithmically. There are these auctions where these ads get sold and the price gets automatically determined in a fraction of a second. So if you have a budget to optimize for your advertising as a company who's trying to hire, and women's attention is expensive, you may end up in a situation where you allocate all of your budget to showing your ad to more people whose eyeballs are cheaper to expose, and that's men. So this is kind of a upside down way how sometimes we have these biased outcomes where there was no animus, and even contrary, there was an attempt to do right by people, but the optimization procedure is just very sensitive to such imbalances, and the optimization procedure by design is going to create these inequalities. Okay, quote by Arvind Narayanan: when a machine learning system uses argmax to select outputs from a probability distribution, and most of them do, it's a clue that it might be biased. That's because argmax select the most probable output, which may amplify tiny data biases into perfectly biased outputs. Okay, and then another point. So hopefully the previous convinced you that it's not just all about the data being biased. Some architectures are actually just sensitive and more susceptible to those data biases than other architectures. Another point, the less usual suspect, the greater system. Predictions are not the same as decisions. Propensity to trust AI, decision subject, propensity to enact recourse, gaming, all of this leads to feedback loops. So there's a lot of steps between decision to collect the data and issuing a decision to a human that are outside of the AI bit, the little machine learning bit. So we need to think about systems holistically. Okay, so here's an example. This is not my slide. The source is at the bottom. Collecting data is where human bias comes in. Labeling data is where human bias comes in. Training using chosen metrics and objectives is where human bias comes in. Model deployment in production, users see an effect, user behavior informs further data collection, and so on. So don't let anyone tell you that it's all about data set and people designing AI systems and procedures are totally absolved of responsibility. That is not true. So fair models is a term that is insufficient. I would argue you should be thinking about fair systems. It's a little bit more complicated than just making sure that your machine learning algorithm satisfies some constraint. The whole pipeline, from data collection to decision, to arbitrage, to recourse, the whole pipeline should be examined. Okay, so what does it mean to be fair? We talked so much about the problems that exist and how clearly there are some issues, but what does it mean to do well with respect to fairness? The key takeaway from what comes is that most definitions are based on the confusion matrix. I'm going to talk to you about what that is. There's no correct way to uniquely define fairness. There are many, multiple, diverse ways. The goal is to make your choices on how you want to measure it, make them explicit, and make your assumptions explicit. Okay, so there are all these terms: justice, equality, fairness, bias, equity. They sound vaguely similar, but are they distinct? And if so, how so? There are these terms like group fairness, demographic parity, individual fairness, equal opportunity. So here's like a quick illustration on the intuitive philosophical distinctions between equality, equity, inequality, and justice. I'll give you a second just to stare at these pictures. And hopefully can kind of penetrate that these are slightly different scenarios, and some people really have kind of normal and ethical preferences for what do they think is fair. Maybe given everybody's same treatment, same opportunity is fair. Maybe giving people same access to something is fair. On the other hand, if their circumstances are different, maybe it's just about equal treatment for everybody, or maybe it's about changing the system so that the equal treatment would result in equal outcomes. So there are all of these slight distinctions. We're going to look into detail about this. So how do people measure unfairness? Here are a few definitions of unfairness or binary classification. We can define fairness by requiring that an AI model prediction satisfy desirable statistical properties. Such definitions may loosely map onto these flavors of philosophical thought. So deontological universalism, virtue ethics, or utilitarian philosophical ethics, or distributive justice like Rawlsian ethics, vaguely map onto these different definitions that I'm going to introduce. A chosen definition may sound right in some contexts to some stakeholders, and they may sound or appear wrong to other stakeholders or in other contexts. And at the end of the day, there's always a conflict of interest whenever AI predictions are concerned. So many such definitions are known to be not jointly satisfiable. I'm going to give you these definitions shortly, but I want you to already take away that typically, depending on which definitions you choose, you unfortunately cannot have all of them satisfied in the same model. Okay, so we're going to use a little bit of notation. X is going to denote all of the various features of individuals that you have in the data based on which you're going to train a model that predicts the outcome Y. And then Y hat is going to be the predictions that the model produces, and A is just one of the features. A is the sensitive attribute, so membership in a protected group like race or gender or age. Predicting means inferring a value that will be used for decision making. So for example, Y equals 1 means this person will default on a loan for the decision should this person be given a loan. And or Y equals 1 may mean this person will fail to appear in court next month if I release them on bail today, or the decision should this person be detained pre-trial. We would like to predict Y in a fair way, meaning that our predictions should not be discriminatory against any particular group, like A equals 1 or A equals 0. That's the sense. Predicting, okay, yes. So Y hat is the indicator of the probability that Y is equal to 1, which is just you're thresholding your probabilities of positive outcome. It's typical. First definition. This is the most common definition of fairness that is most typically used both in algorithmic context, audit, and in legal scrutiny of algorithms as well. It's called demographic parity or statistical parity. And what it literally is a requirement that these two probabilities are either equal or within a certain threshold of one another. So on the left-hand side, you have probability of predicting positive outcome conditional on one demographic subgroup. And what you want to call this algorithm fair is that that probability is the same as the probability of predicting the same outcome for the other demographic subgroup. So it requires that a decision is independent of the protected attribute. So members of one group, I don't know, females and non-females, they have the same average probability of getting assigned positive prediction. Okay, equality of opportunity, very similar. I highlight in the same color similar components of it, but now you're adding an additional condition. You are conditioning on the true outcome. Imagine that you have the training data where you know the real outcomes of the people from history, right? You know which people who were released on bail or released pre-trial went on to reoffend. So now you're adding an additional condition. You want the probability of predicting that this person will reoffend, conditional on them being, I don't know, Black, and on the fact that you did see that in the future they did in fact reoffend, to be the same as probability of predicting reoffense for the non-Black demographic group. Again, conditional on these people did reoffend. So you want the same as you did in the left, you want the demographic parity, but now just for people who actually did have this outcome, in fact. Okay. Third definition, equalized odds. Here, instead of conditioning on one class of true outcomes, like in the previous case, you cared about this negative outcome. You wanted equality for people with the negative outcome. Now you want the equality across outcomes. So this essentially for binary classification, this is two statements. One where the line in black has Y equals 1 on both sides, and one where it has Y equals 0 on both sides. So given the outcome, attribute A provides no further information about prediction. That's how you read this. Calibration. So what happens here is you flip the conditional statement you had with the probability, the event of the probability of which you're estimating. So here, given the prediction, attribute A provides no further information about the outcome. If A is on average informative of Y, we cannot reconcile these two definitions. So if you want to measure the fairness of your model using this definition 3 equalized odds versus calibration, it turns out you cannot in general have both. These are all of the other definitions of fairness that exist. You don't need to pay too much attention other than just appreciating that there's many of them, and there are more coming out every day. Most definitions are based on the entries in the confusion matrix, and there are these impossibility theorems that tell you that many of these definitions are mutually unsatisfiable at the same time, so it's impossible to reconcile them. So there is no correct way to uniquely define fairness. The goal instead is to make your choices and assumptions explicit. Say what you are measuring, say why you are measuring it, and what assumptions are you making. Okay. I want to talk a little bit about stakeholders and why whose interest you have in mind will matter a lot in which definition you might think is the best for you to use as you're measuring fairness or unfairness of your AI. So on the right, you have the confusion matrix. Basically, I don't know how familiar you are, but I will just introduce it. Say it's a binary outcome. Someone either defaulted on a loan or did not, and we predicted that they either would default or we predicted that they would not. If they did not default and we predicted that they wouldn't, no problem, right? That's a true negative. If they did default and we also predicted that they would, that's a true positive, also not a problem. Now, problematic cases are these red entries in the confusion matrix. One of them is that we predicted negatively. We thought this person would not default, but it was a false negative. In fact, they did default. And the other type of error is we predicted that they would default, but actually in reality, they did not. So majority of models are optimized typically using the harmonic mean between precision and recall. So there's like some way of balancing how many of the false positive errors and false negative errors you want. However, in social contexts, wherever humans are concerned, different types of errors carry very different ethical weight. What I'm saying is that these false positives and false negatives do not matter equally in most settings where humans are concerned. So from whose perspective are you trying to evaluate which errors matter the most? Consider recidivism risk prediction. Which type of error is costly for the decision maker? The decision maker here is the Department of Justice or the law enforcement. Do you think they care more about releasing a person who ended up reoffending, or do they care more about detaining a person that in fact would not have committed any crime? You probably have an answer in mind. Yeah, please go ahead.
I was gonna say, yeah, I mean, they don't want to put innocent people in jail. So would that be a false positive?
So yeah, let's make it clear. Say a positive decision is I predict that they would reoffend. Continue your thought.
Well, I was thinking, I guess the justice system would rather be wrong and have someone reoffend than put an innocent person in jail.
God bless you.
No, is that not the case?
I feel like unfortunately, yeah. So I wish. The reality is that a lot of the time, the budget for our kind of law enforcement is decided based on things that are unfortunately more often associated with the other type of error. So what is a big problem for police is if there's a news title in the New York Post or wherever on TV about someone committing a crime, and then people find out that this person has been arrested before, and then there are all these questions, why did you release this person? You are not doing your job. If they put someone in jail and that person was not really a threat, no one ever finds out. The only people who suffer, I shouldn't say the only, people who suffer are this very person who got erroneously put in jail and the communities. There are some communities where people are put in jail left, right, and center without strong justification. Those communities suffer, but the police department doesn't. They still look good on paper. So thank you for bringing up which one is which. Let's walk through this. So if the positive decision is we predict that there is a high risk this person will reoffend, then a false positive is when the algorithm predicted they would reoffend, and actually, based on this prediction, the person was detained, not released. But the counterfactual was that they were not gonna be harmed to anybody. Now, a false negative is where we predicted negatively. We said this person would not reoffend. They got released, and then a crime occurred. So, from the viewpoint of law enforcement, majority of the time they care far more. Their budget is on the line for optimizing one of these types of error, and that's the type of error that we just talked about. So, thank you so much for your comment. So, yeah, they care to not release people who will reoffend. And what about the defendant? It's exactly the opposite, right? They care much more about not being erroneously put in jail. And what about the public? This is where it gets tricky. Depending on your political affiliation, some people care much more about not detaining innocent people versus making sure we do detain all the ones that are going to create criminogenic situation, right? And then if you take whole communities, like ethnic communities, racial communities, class communities, they care a lot more also about the rate at which their community gets locked up and how many people, how many children grow up without, significant family members because so many of them are incarcerated. Bottom line, different stakeholders for the same AI have very different priorities, but only one of the stakeholders is designing the AI. So, more people should be at the table when talking about which errors should be optimized for. Different example, considering AI housing assistance allocation, which type of errors is most costly for the decision maker, which is the HUD department, or for the applicants, or for the public? Same, right? Typically the answer is not the same ones. Different stakeholders care about different things. This is where we do the breakout rooms. I would like for you to take a screenshot of this in case, you want to refer to it in your breakout rooms. So here's an exercise. We're going to choose a business target for AI classification. So meaning, what are you trying to predict? You're going to think about what could be a sensitive or prescribed attribute. Is it race? Is it age? Is it disability? Is it gender? Whatever it is. What would be an undesirable, unfair outcome? And then I would like for you to define a false positive, define a true positive, define a false negative, define a true negative, and then think about which type of errors, so false positive or false negative, is the most costly, which type of error is the most important to avoid, depending on the stakeholder. So hopefully I could convince you that depending on whose interest we keep in mind, the costs are vastly different. And people who design algorithms typically serve only one of these stakeholders and not all of them. So it's important for people to have a seat at the table. Okay, let's get slightly more technical. Overall accuracy versus false positive and false negative rates. An example is correctional offender management profiling for alternative sanctions. That's the algorithm that I showed in the first slide. That's the problematic one. The target that people are trying to estimate with AI is risk of recidivism within 2 years. And the model inputs are personal attributes of the people under consideration, so-called offenders, right? The criminal history, substance abuse, all of that stuff. So the overall accuracy of this model is 68%, but among the Black people, it's 67%, among the white people, 69%. You could also say, okay, no problem. Overall accuracy for Black people and for white people seems kind of like within a reasonable margin of error one of another. Doesn't look bad. However, prediction fails different for Black defendants versus white. So overall accuracy is comparable. But once you start breaking down overall accuracy, instead of overall accuracy, looking at false positives and false negatives, you see that labeled high risk but did not reoffend, so a false positive, for white is 23%. This type of error occurs 23.5% of the time. For African American, 45%. And then labeled low risk yet did reoffend, so a false negative. For white people, 47.7, for African American, 20. This is another vignette on how looking just at the overall accuracy and comparing it from class to class is misleading. You need to break it down. There was a rebuttal, there was this agency. I'm going to skip through this. Basically, depending on what you're choosing to measure, you can say, oh, our algorithm is very fair, or no, it's horrendous. These measures are typically irreconcilable. Okay, so can we have a score with no discrepancy on these measures? No, we cannot. This would only be possible if recidivism did not vary by race in real life. So currently, recidivism does vary by race, as many people will tell you. So we cannot have test fairness and the same rates of false positives and false negatives regardless of race. So this hinges on this assumption that currently recidivism does vary by race. Currently, like people of different classes, like default on their loans at different rates. So as long as that's true, you cannot have reconcilable fairness measures. But is that really true? This slide is lifted from Kristen Loom's presentation. It's just so perfect that I straight up borrowed it. What is predictive policing? Predictive policing uses police records to learn patterns in the occurrence of crime, is what you will typically hear. Using these patterns, the computer then predicts the most likely locations of future crimes. Additional police are then dispatched to the locations with the highest predicted rate of crime, thus preventing the crime that would have occurred from occurring or catching criminals in the act. Or, if you look more closely, predictive policing, as in the top left corner, uses police records to learn patterns in the police records. Using these patterns, the computer then predicts the most likely locations where crime will be detected by police in the future, because they will be sent there. And additional police are then dispatched to the locations where the highest predicted rate of crime, finding crime that they wouldn't have found otherwise. So again, bottom line is that this argument that in real life, rates of recidivism vary, rates of default vary, again, it's a question of what you're choosing to measure, where are you going, where are you sending all of your efforts to go and measure things. If you're going to send police only to certain neighborhoods, yeah, you're going to find crime. So which definition has legal power? Title VII of the Civil Rights Act. This is very important. Disparate treatment and disparate impact are the two doctrines that we currently have in the American law that govern biased decision-making. Now, this framework was written way before the age of AI, or way before the age of computerized prediction at large scale, but it still generally applies today. So disparate treatment refers to intentional discrimination, where people are treated differently depending on their membership in a class. So a decision considers if you're a member of this class and then treats you differently. Disparate impact, on the other hand, refers to systematic differences in outcomes, not necessarily the procedure for how decision was arrived at, but the outcomes for members of different classes. So maybe your race was not considered, or your gender was not considered, or your age was not considered, but as you then look at who got predicted what, you see the discrepancy. And here you just have demographic parity that I showed before. There's a three-step procedure that currently companies need to follow if they are ever brought to justice for a case of accusation of bias. The plaintiff must first prove that a specific employment or housing practice or whatever practice causes an adverse effect. This is the burden that's on the plaintiff. So whoever tries to find justice needs to assemble a lot of evidence first that establishes that people of this group, on average, get certain predictions far more frequently than people of that group. Then the employer must then show that the practice was undertaken as a business necessity or is manifestly related to the duties of the job. Even if you do show that your decisions affect groups differently, as long as you can say, hey, but I have to consider it because the accuracy of my model would be lower if I didn't, you're good, according to the law. And then the plaintiff must then demonstrate that the employer could have used a different technique that leads to less unfairness, but similar accuracy. Again, considering that right now all of these algorithms are proprietary, nobody has the privilege of discovery of how the algorithms work, which models are used. This is all protected information that constitutes kind of business trade secret. Good luck trying to establish the argument that is required here. So, but this is currently how the law works. Mitigating unfairness, I'm just going to gloss over this very quickly. First idea, just don't consider race. Don't consider gender. Don't consider it in your model. Don't supply it to your model. Problem is proxies. We already talked at length with the example of the resumes, how even if you remove all this information, like Natalia said, you might still get it to leak through other features that are associated with both the outcome and membership. So, for example, race has an impact on charges, prior arrests, residential stability, employment, et cetera, et cetera, et cetera, et cetera, all of which ends up being inputs in the pretrial release. So some solutions that were proposed is just to flip the labels as you're doing the training. So if you have like class imbalance, create more synthetic features. This is all kind of very problematic from the regulatory viewpoint. Another idea is to obfuscate the effect of the sensitive features on proxies. So first, you're going to fix all of your features one by one to get rid of that association. Really hard to do, and you're going to lose some accuracy. You can use regularizers in your machine learning. So just introduce a little penalty that the machine learning model kind of feels bad about producing too much unfairness. So it's trying to simultaneously optimize the parameters to get both high accuracy and lower unfairness. Yeah, so basically here's your typical machine learning objective. You just add this regularized term that increases your penalty if you have demographic disparity. And then there's fair representations, which is when you're trying to forget information about the sensitive feature by projecting everything into some subspace that in such a way that you forget. It's impossible for you to reconstruct the value of the sensitive attribute. Then there are more kind of qualitative methods like checklists, data sheets for data sets. Motivation is that you need to register and make it transparent to external auditors, all of this information that's relevant for evaluating the unfairness and where it comes from. So for what purpose was the data created? Was there a specific task in mind, or did you just collect the data because you could? Was there a specific gap that needed to be filled? Who created the data set? On behalf of which entity? Who paid for it? And so on. So just basically as much information as much transparency as possible. Collection, process, distribution, maintenance, and so on. Nutritional labels from Julia Stojanovic, who's a professor at NYU Center of Data Science. Basically facts about your model. What are the mean values? What is the distribution of the two demographic groups? How does it do on fairness metrics? Again, the idea is transparency. Model cards, similar to this, where you just really, really scrupulously go through all of the choices that are invisible, like choice of threshold. Which metric did you choose to optimize? Did you optimize for this error, that error? Make it clear. And so many classify these as audit tools, but they can and should be used in development. So this is something that's useful for the machine learning designers to have in front of them as they're designing. Okay, I think I'm going to just skip this and go straight to the conclusion. A few useful intro links. I'm going to distribute the slides. You can play with some of these examples on the websites that have either important case studies or implemented the definitions that I mentioned to you that you can play around with and see how you can achieve more or less fairness. And I'm open to your questions. And thank you so very much for your attention.